without further ado, I'd like to introduce our first speaker, John McCartney, who's going to be talking about heat exchange and heat storage in urban subsurface infrastructure.
Sorry, it coincided with his nap time.
We are a family-friendly event.
Thank you. Thank you for having me. Hopefully I'll be the only person speaking during this session. So today I'd like to talk to you about heat exchange and heat storage in urban subsurface infrastructure. The motivation for this is that buildings consume a very large amount of energy, and out of all the different ways that buildings consume energy, the heating and cooling systems are one of the major sources. So thermal energy is an important thing that we need to deal with in urban locations. So some of the key questions that we have for society in general are: how can we obtain thermal energy sustainably when we want it? Sometimes when thermal energy is available, we don't necessarily want it. So how can we store it? And if we don't want it, how can we get rid of it in a way that is minimizing the effects of disposal on other people? And finally, how can we use thermal energy more efficiently? How can geotechnical engineers play a role in all of this? The first thing is that the subsurface is a very good insulator. It's a very good heat storage medium, has a good specific heat capacity. And we always are installing things down in the ground: foundations, tunnels, retaining walls. And these are all pathways that we can use to exchange or transfer heat into the ground. So I like to think of thermal energy as three different media. So the first would be a resource. In this case, it's something that we want to have. So we need to use this for conditioning our spaces. We want to access naturally occurring heat instead of burning fossil fuels or electrical resistance heaters to get that heat. So if we can harness that heat from the sun, that's one very good sustainable heat resource. Second, thermal energy can also be a waste. We need to reject heat from buildings for cooling. Sometimes we can move this heat around to different places in the building because maybe the side of the building that's in the face of the sun is hot, the other side is cold, so we can transfer it inside of the building. But we also have industrial processes that are hot and we want to get rid of heat. But if there's a large amount of people in an urban area, they're all trying to do that at the same time, they could start to interfere with each other, and you could reduce the efficiency of other systems. So one thing that's kind of interesting that I don't think people have looked at very much is using thermal energy as a tool. And as geotechnical engineers, we'd like to have as many different tools as we have to solve problems as they arise. So the first could be to improve saturated clays using thermal consolidation. Soils are a weird medium that when you heat them, they don't necessarily contract like steel and concrete. The water is going to expand more than the soil drains, and you could have pressurization that's going to cause a consolidation effect, and you actually get contraction during heating for some situations. You could also use heat to dry soils, and we know that dry soils are going to have higher effective stress, and they're going to be stronger. We could also do interesting things. We could use heat to improve contaminated ground. Many times when you're in urban settings, you're going to have previous industrial processes that have contaminated the ground, and we could use heat to get rid of that contamination. We could also modify processes in landfills. Landfills are often very close to urban areas, and we often want to reuse that same space in the landfill, put more waste in that same location. And another interesting thing that I talked to somebody about this morning is using heat to de-ice roads. In New York City, they still use salt for a lot of de-icing. That causes a lot of effects with your subsurface utilities. So what is the tool we're going to use as geotechnical engineers to transfer heat? We're going to use the ground source heat pump system. These don't generate heat, but they actually move it from one place to another. We're going to exploit the heat pump cycle, so we need to work with mechanical engineers. This is the same thing that you're having on your air handler or your window unit for air conditioning. But instead of dumping the heat into the outside air, we're exchanging heat to a fluid circulating inside of a pipe that we're going to embed inside of our concrete subsurface infrastructure. So at the end of the day, you have some convective heat flow inside of that pipe, but you're going to be having conduction into the surrounding soil. And if you have enough length of the pipe embedded in your concrete, it can work anywhere. So it's not just a tool that can be used in cold environments or in heat. This is just a close-up of how we exchange heat from a refrigerant going through your heat pump cycle and water. You can see the baffles in the top left picture. The average ground temperature usually is equal to the average air temperature because the ground is absorbing the solar energy, storing it in the ground. So once you go below a certain depth, the temperature is relatively constant. So when we want to heat our building, we're going to put cold fluid into our circulation pipes. It's going to come back warmer, and we're going to extract that to heat our building. When we want to cool our building, we're going to put hot fluid down that's hotter than the ground temperature. These heat exchangers are going to come into many different configurations. You can see the coil configurations, horizontal loops, vertical loops, energy piles are one very good application. So with that, I'm going to quickly go through 5 of these different examples of ways that geotechnical engineers can use heat exchangers. I could talk about each of these for an hour, so I'm just going to quickly go through some different slides. We could talk about it later. The first are energy piles. These are a pretty tried and true approach right now, but they're still very slow in being implemented in the United States. Here we're putting heat exchange pipes on the inside of our reinforcement cages. You're bringing all the pipes up to the surface, manifolding them all together, sending the pipes to a mechanical room, and then you have a heat pump that's going to be there. The big challenge here is that you need to have some interaction between the different trades and some planning. So you can't just do this as a geotechnical engineer. You need to work with mechanical engineers at the beginning. But it's been used in Europe, UK, Japan, very widely. Just a quick demonstration of this system. We installed, converted 2 energy piles under a building in Denver into energy piles. The nice thing is that they were already going to be putting in conventional ground source heat pump systems, so we didn't have to completely build our own system. We chose 2 different foundations, one under the edge of the foundation, one under a central column. In Denver, they have this Denver blue shale. All of them are rock socketed down into this layer. And we have about 6 years of data from these, 5 years of data from these piles. And so this is showing the heat exchange over time. You can see the entering and exiting fluid temperatures. Sometimes during the winter, you're actually cooling the buildings because Denver can have sunny days in the winter. But we're getting about 91 watts per meter of heat exchange per heat exchanger length. But the interesting thing that happens is that when you're exchanging heat between your building and your foundation, the foundation is changing in temperature, and those foundation temperature changes are going to lead to stresses and strains. The foundation is going to want to expand when you heat it. Those are going to lead to stresses in your pile, and you want to make sure that those are not going to cause problems. In this particular situation, over those 5 years of operation, you can start to see the strains not following a very stable trend like we noticed in the temperatures. You can see some data missing in the later years, around the time that I moved from Denver to San Diego. But you can still see the strains are starting to move up. And one thing we noticed is that the temperature was affecting the ground around the piles. We're end up having a thermal drag down process. And that drag down process was adding to the stresses that we're getting from combining the mechanical and thermal loads. We can also integrate the strains that we measured in the pile and get our displacement profiles. And here we can see that the displacements we're going to get are not really going to cause architectural damage to the building, even when you consider differential movements. Kenichi Soga has done a very nice review of what would be the case if we put energy piles all throughout a city. And you're going to use different amounts of heat depending on the different applications of the buildings. You can see the different categories of buildings on the left. And then looking at if all of them were trying to use this at the same time, you can see that there are several regions that are red, which means that we're using too much of the resource. We don't have enough capacity for the demand. So these sorts of maps, if everybody starts to adopt this technology, we're going to need to generate. We also have some other technologies we can use. Instead of having this fluid circulating through the system, we can actually use a heat pipe, but that's still a long ways off. Just one quick note before we end. So solar thermal energy is a very good resource, but it's only generated during the day. Many locations in the north, like in Canada and Denmark, which aren't known for being sunny places, are using these sort of solar thermal energy generation. And they're using these in district heating systems, which are ideal for urban settings. But we need to store it. So one way that you can store it is in these borehole fields or energy pile fields. You start to inject heat in the winter, in the summertime, you let it rest, and then in the winter you extract it. So you're using the ground as a battery. And we've shown that this works in simulations. So over time, you start to, even though you're always losing heat to the surrounding soil, it's building up. And the efficiency of operation increases over time. One problem is if you put them in saturated soils with groundwater flow, it's going to take that heat away. So you need to understand your subsurface geology very well before you can use it. So I'm advocating putting these into the unsaturated soil layer where you don't have very much groundwater flow, but it has very good thermal properties for storage. So we built one of these systems in San Diego, 15 boreholes, smaller than an actual operation system. But we collected heat from these solar thermal panels, stored it in a temporary hot water tank, injected it into the ground, and we, over the course of a summer, injected about 60 gigajoules of heat into the ground, heated up our soil, and let it recover. So with that, we were able to heat up the ground, and this is a good example of how we can use our soil infrastructure for more purposes than just supporting projects. So thank you.
So John's given us two nice examples of things at rest. So any quick questions? We have time for one short question.
100 years ahead of somebody earlier, what do you foresee? Are there any issues with our batteries getting drained?
Unless the sun stops working, that would be one problem. But
As far as injecting heat into the ground?
so the nice thing is that you inject the heat, it starts to escape, and it can never escape very far. So your efficiency is going to gradually increase over time, because that you're going to inject and extract. Inject and extract. It's going to be like blowing up a balloon more and more. I think it's going to always become more efficient over time.
So just as a note, I'm funding University of Utah and Idaho National Lab to try to use develop a geothermal battery, which would store gigawatt hours. The preliminary results are that it's extremely efficient.
Yeah. I saw that project.
All right. Thank you very much.
Cool. Thank you.